Hello, everyone. I'm getting ready to work a problem with capacitors. I actually have in this case, I have a capacitor that's air-filled, a parallel plate capacitor, and its initial separation is Z. And then I'm going to separate it until the final separation is some number N times Z. And what I want to do is calculate the change in energy stored in the capacitor and going from air-filled at Z to air-filled at NZ. And then I'm going to calculate the work done in actually separating those capacitors while a battery is connected. So let me start off by sharing my screen so you can see the actual statement of the problem. So it says, consider an air-filled parallel plate capacitor with an area A and separation Z. If the plates are connected to a battery of voltage V and the plates are pulled apart until the separation is NZ, A, what is the change in energy stored in the capacitor? And that's what we call delta U. And then part B is, what is the work done in pulling those plates apart? And we call that W. So I'm going to go ahead and calculate that. So I think you can remember all those symbols, but it's pretty straightforward. Notice I'm leaving the battery connected the entire time. So let me stop sharing and start going to my document cam. So the way this works is initially we have a potential energy or energy stored in the actual capacitor. Let's make sure this is off. Yeah, that looks pretty good. We have an energy initially U1, which is 1/2 C1 V squared, and that V doesn't need a subscript because we're keeping the battery connected at all times. Because of that, that's just 1/2, and then of course the formula for capacitance of an air-filled capacitor is epsilon 0 times A. Notice I actually had on the original problem the surface area of the parallel plates was A, and then of course it's divided by Z, the distance apart, and then of course that multiplied by V squared gives us 1/2 epsilon 0 A over Z times V squared. That's our U1. Our U2 is 1/2 C2 V squared. Of course, this time the C has become epsilon 0 A over N times Z. And of course, N could be like 2 or 3, or it even could be a fractional number like 2.57 or whatever. The key point is I'm getting a generic result here that works for any multiple of Z. You might even call it a different separation altogether, just call it L, and then you'd have another expression for L just by replacing the NZ. So this is clearly going to give us 1/2 epsilon 0 A over Z V squared times 1 over N, which is just basically 1 over N times U1. That's kind of a nice way to put it. So that the change in potential energy, or the change in energy stored, U2, is actually, or excuse me, delta U is supposed to be equal to U2 minus U1. So U2 is going to be 1 over N times U1 minus U1, which I think you can tell is just U1 times 1 over N minus 1. Obviously, getting a common denominator would make this a little nicer. And I'll end up saying it's equal to 1 minus N over N times U1. So that's our answer for part A. Delta U is equal to 1 minus N over N times U1. Okay, so for instance, in the case of N equal 2, like I doubled the separation, that would of course be 1 minus 2 over 2. 1 minus 2, of course, is negative 1, so this would be negative 1/2. N equal 3, it would be negative 2/3, and so on and so forth. Now, to calculate the work done, this is part B, it's slightly different. Work, of course, is equal to the integral of f dot dl, technically a line integral there. I'm going to substitute for f the force. I'm just going to assume that's acting basically parallel / anti-parallel to the actual faces. So, or I should say perpendicular to the faces. And we're just going to pull them straight apart. The force should be, in fact, the charge times the electric field. So I'll write equals integral of Q times E times dz, where z is the direction along which the separation is measured. Now here's the deal. I'm actually calculating the electric field caused by one of them multiplied by the charge, say, on the other one, so that I'm not actually using the typical electric field strength between two capacitors, which is sigma over epsilon naught. I'd actually have to use something like the sigma over 2 epsilon naught, because I'm actually calculating the force due to one field and the charge due to the other one, or the charge due to the other plate. So I should say force due to one plate and then the electric charge due to the other plate. So in this case, I'm going to say Q is equal to C times V. And I'm going to say V or E is equal to V over 2Z. Normally, we would say the electric field between the plates is V over Z, but I know only half of that is actually acting on one of the plates, because the other plate can't apply a force to itself. So I write this as 2Z over Z, over 2Z, and then times dZ. And of course, when I integrate that, I get 1/2 V squared times the integral of epsilon 0 A over Z times 1 over Z times dZ. So this epsilon 0 A over Z is the capacitance. The V times V gave me the V squared. The 1 over 2 gave me the 1/2. So I've got epsilon 0 A over Z is the C, and the 1 over Z comes from this guy. So I'm now able to integrate this all in terms of dz, and basically I just get 1/2 epsilon 0 A times V squared times the integral of dz over Z squared. And I'm actually integrating that from Z equals Z up to NZ. When I do that, that actually becomes negative 1/2 epsilon 0 A V squared times 1 over NZ minus 1 over Z, which allows me to factor out that actual Z. So I get negative 1/2 epsilon 0 A over Z times V squared, again, times 1 minus N over N. And I think you see that is, in fact, the opposite of delta U. So I see work is equal to the negative delta U, which is what we expect. What we were calculating is the work done on the actual work done on the actual capacitors, and of course that's equal to the negative of the change in potential energy. If you actually went from low potential energy to high potential energy, you'd actually have to put work into the system. And in fact, since this actually came out to be a negative, we know that the potential energy actually went down, and therefore the work should have been a negative quantity. So I think that's a pretty good little introduction to capacitance and capacitors, parallel plate capacitors being separated. I want to show you the problem once more. Again, the results delta U is 1 minus N over N times the initial energy stored, and the work turned out to be equal to exactly the same thing, but differing by a negative sign. So let me share the screen to show you the problem one more time. So that was the actual problem. And I hope this was helpful for you in trying to learn how to work problems in capacitance. Have a good day.